In today's video, we will see the derivation of the equation for loss of head due to sudden enlargement. This is a type of minor energy loss which occurs because of the change of velocity of the flowing fluid in magnitude or direction. Here, we are having this pipe as shown in the diagram, which is having sudden enlargement. And due to this sudden enlargement, the flow will get deaccelerated and eddies will start to form in this region. Here in this region and in this region. As suddenly the pipe enlargement took place, the flow got deaccelerated and eddies formation took place. Now here we are considering two sections, the section 1-1 and section 2-2. Section 1-1 is before enlargement and section 2-2 is after enlargement. P1 is the pressure intensity at the section 1-1. P2 is the pressure intensity at section 2-2. V1 and V2 are the velocity of flow at section 1-1 and 2-2, and A1 and A2 are the area of pipe at section 1-1 and 2-2. The flow in the pipe occurs due to some force, and this force acting in the direction of the flow, we are denoting it using Fx. Then we are having pressure intensity of the liquid eddies on the area A2 minus A1, which is here where the eddies are formed. There we have the pressure intensity, which we are denoting it using P dash. And the loss of head due to sudden enlargement, that will denote it using He. Now we'll apply the Bernoulli's equation to the section 1-1 and section 2-2. The Bernoulli's equation is P by rho g plus V square by 2g plus Z is equal to constant. For section 1-1, it will be P1 by rho g plus V1 square by 2g plus Z1 is equal to, for section 2-2, it is P2 by rho g plus V2 square by 2g plus Z2 and plus the head loss that we'll consider due to sudden enlargement, which is He. Now as this pipe is horizontal, Z1 will be equal to Z2, so it will get cancelled out. We'll be left with P1 by rho g plus V1 square by 2g is equal to P2 by rho g plus V2 square by 2g plus He. Now we'll write making He as the head of the equation. Therefore we get He is equal to P1 by rho g minus P2 by rho g plus V1 square by 2g minus V2 square by 2g. Let's see what all forces are acting between the section 1-1 and 2-2. Here the first force will be pressure force on the section 1-1, which is P1A1. Then as eddies are forming here, we'll have the pressure force, which is P dash into A2 minus A1. And here on the section 2-2, we'll have the pressure force, which is P2A2. For P2A2, we'll have negative sign because it is in opposite direction to the direction of the flow. Therefore, we'll write Fx is equal to P1A1 plus P dash into A2 minus A1 minus P2A2. When experiment has been carried out on a pipe having sudden enlargement, it has been found that P dash is equal to P1. Therefore, we'll just substitute this here and we get Fx is equal to P1A1 plus P1 into A2 minus A1 because P dash is equal to P1 minus P2A2. Then when we'll expand this, which is P1A1 plus opening the brackets P1A2 minus P1A1 minus P2A2. P1A1 will get cancelled and we'll have Fx is equal to P1 minus P2 into A2, as we took A2 common. Now we'll consider the momentum. Change of momentum per second is equal to momentum of the liquid per second at the section 2 minus momentum of the liquid at section 1. Firstly, we will derive the equation for momentum of the liquid. Momentum is equal to mass into velocity, and density is equal to mass upon volume, from which we can write that mass is equal to density into volume. Therefore, we can write that mass is equal to rho into dV by dt, which is we have considered the change in volume. Then we have one more formula, which is volume is equal to discharge into time. And here dV by dt will be equal to discharge. So we can write mass is equal to rho into Q, and Q is A into V, which is area into velocity. Therefore, we get this formula for momentum of the liquid, which is rho A1 V1 square. From this, let's write the momentum of liquid per second at the section 2. That will be equal to rho A2 V2 square. And for section 1, the momentum of the liquid per second will be equal to rho A1 V1 square. Therefore, we got the change of momentum per second as rho A2 V2 square minus rho A1 V1 square. Also, we know that the continuity equation gives us that A1 V1 is equal to A2 V2. Writing this, making A1 as the head, we get A1 is equal to A2 V2 upon V1. Now this value of A1 that we got, that will substitute here in the change of momentum per second equation. This will write it as rho A2 V2 square minus rho into A2 V2 upon V1 into V1 square. Then we get rho A2 V2 square minus V1 gets cancelled. We get rho A2 V1 into V2 is equal to rho A2 into V2 square minus V1 V2, as we took rho into A2 as common. Then we are having the net force, and this net force is equal to change of momentum. We have already found both of these things. The net force we had got P1 minus P2 into A2, and change of momentum we have got it as rho A2 into V2 square minus V1 V2. Then here we can see that A2 we can cancel it. We'll be left with P1 minus P2 upon rho is equal to V2 square minus V1 V2. We'll just divide this both sides by G. So we get P1 minus P2 by rho G is equal to V2 square minus V1 V2 upon G. We have got this equation for He. We'll substitute the value of P1 by rho G minus P2 by rho G from this equation. Let me just write it here. He is equal to P1 minus P2 by rho G plus V1 square minus V2 square by 2G. Therefore, He will be equal to V2 square minus V1 V2 by G plus, separating the LCM, which is V1 square by 2G minus V2 square by 2G. Therefore, we can write He is equal to V2 square by G minus V1 V2 by G plus V1 square by 2G minus V2 square by 2G. As we are having 2G, here also we'll multiply it and divide it by 2. Therefore, we get He is equal to 2V2 square by 2G minus V2 square by 2G. It will be V2 square by 2G minus 2V1 V2 plus V1 square, and 2G we took it as the LCM. This is the formula, this is the expansion of A minus B whole square. So it will be v1 minus v2 whole square upon 2g. Therefore, we get HA is equal to v1 minus v2 whole square upon 2g. This is the equation for loss of head due to sudden enlargement, and this equation is also known as the Borda-Carnot equation. Let me just summarize it. We started by applying the Bernoulli's equation to the section 11 and 22. Then we found the force acting on the liquid between the sections 11 and 22. Then after we found the change of momentum per second, and then we applied the continuity equation, and then we compared the net force with the change of momentum. From this we derived the equation for loss of head due to sudden enlargement. Thank you.